The ideal gas law is the last of our gas variable relationships, and so far we've looked at temperature, volume, and pressure, and this time we're adding one more variable, amount, to the mix, and we will represent amount with lowercase n into our gas law equation. So if you remember back when we were talking about amount a couple of units ago, we described it as the quantity of chemical particles, and we measured that in moles. So the same thing is true for our ideal gas law. Whenever we are plugging in for n, it must be measured in moles. Now remember, there's a relationship between grams and moles. Molar mass, which is the mass on the periodic table for each element. And so if there is an amount given in grams, or a mass, that can be plugged in for n, but you must convert it to moles first. So just put a little note here, convert grams to moles using molar mass, mm standing for molar mass. If needed. We're actually going to focus on this on Wednesday because I know it's been a hot second since we've done molar mass. So we will focus specifically on using it for Wednesday's math skills. Now let's talk a little bit about this idea of an ideal gas. And ideal means fake, right? It's a perfect picture. And so this is a concept that scientists have made up of a hypothetical gas to try to make some calculations easier. And so the assumptions that we make for this hypothetical gas is that it's empty space and that there are no forces between particles. And the reason that they make these assumptions is because it makes calculations easier. We don't have to go into higher level math and physics concepts in order to describe the gases. It gives us a ballpark answer, but it's ideal. It's not perfect to real world. It's because gases are not ideal in reality. They are not empty space, and there are forces between particles. And so if you were to continue chemistry in the future into like higher level physical chemistry, there is a more complex gas law relating amount to temperature, volume, and pressure, where it's not ideal. And it's more of a real world gas. But for our purposes, we are going to assume that all gases behave like an ideal gas so that we can do these calculations. And so this idea just makes calculations easier, and we can plug into our equation and get a ballpark answer. It may not be the perfect value because we're making these assumptions, but it's close enough. So for our ideal gas law, we are going to be relating pressure, volume, temperature, and amount in a single equation. And that equation is PV, looks like a Boyle's law, equals N, there's amount, R, this is a constant that relates all of the variables together, and T. So we'll talk about R in just a second in this last box. But P is pressure, and we will be only plugging in either atmospheres or kilopascals. Those are the only options for pressure when plugging into the ideal gas law. And whichever one you use is going to determine which R value will be used as well, which we'll talk about again here in a minute. Volume is our V. That's always going to be plugged in liters. So if you have milliliters, you must convert it to liters in order to plug it in to the equation. N, we've already discussed, is the amount, and this needs to be in moles. And while we're talking about amount really quickly, if you remember back to the guy who figured out moles, his name was Avogadro, and he has a gas law called Avogadro's law that shows amount and volume are directly proportional. And so that's why it's on the same side as temperature over here and opposite of pressure and volume. Because if you think like Charles' law and Gay-Lussac's law, those are also direct relationships, but to temperature. And it should make sense, right? But this one's kind of overlooked because it's pretty common sense that as you have more molecules, that you will take up more space for the amount of gas you have. So more stuff, more space. We don't spend a whole lot of time studying Avogadro's law like we do the other three. However, it is just as, valid as the other three. So just a little note there. Then we have, I'm going to skip R for a second. T is our temperature. And just like with all the other gas laws, you must plug in Kelvin. So really the only wiggle room you get is for pressure. You can plug in atmospheres or kilopascals, but those will affect our ideal constant, R. So in this equation, R is a constant ratio by which pressure, volume, amount, and temperature are related. And so this was discovered empirically, which means in lab, to find the ratio of how they are all related at all times, because they are all proportional to one another or inversely proportional to one another in the case of pressure and volume, like we've studied in Boyle's law. So our ideal gas constant is R, and it is a constant ratio relating our other variables, pressure, volume, temperature, and amount. And so there are two options for our R value, and it really depends on the units that you are using for pressure, because they have to be relating the correct units into our equation. So if we are using atmospheres as the pressure, then the R value you will be adding into the equation is 0.0821, and the unit for this is liter atmosphere per mole Kelvin. And this should make sense if you were to arrange the equation for R. I'm just going to do that really quick here. R equals, you would get PV over NT. And so our units here are representing this. Granted, they're in a different order. They have volume, then pressure, and then mole Kelvin. So the top one is different in the order, but the units are representing what is being plugged in. So we're plugging in liters, we're plugging in atmospheres, moles, and Kelvin. So that is our relationship between all of our units. Double check which units you're using. And the reason that we only care about pressure units when we're deciding our R value is because all the rest have to be only one unit. Volume is always liters, temperature is always Kelvin, and amount is always moles. So if it's kPa for our pressure, then your R value is 8.31. And this time now your unit is liter kPa mole Kelvin. And those dots I'm putting in are just like multiplication signs, but so that it's not all bleeding together. And you can see the individual units, but we just put dots there to show they're being kind of multiplied together, just like numbers would be, but with units. So that's our R value that you plug in depending on the units that you apply. All right, so let's look at the examples. First, we have just some unit analysis, determine if it's pressure, temperature, volume, or amount. This looks very similar to something we did in our bell work, I think, but now we have amount as a possibility. And then circle the units you can plug into the ideal gas law equation, because it is picky and can only use certain units. So let's go ahead and do this. You pause, try this on your own, and then start it back up and see if you are correct. All right, hopefully you've done it. So kPa is pressure, degrees Celsius is temperature, atmosphere, pressure, volume, grams, this is representing amount, but you would have to convert to N, or convert to moles in order to plug it in. Millimeters of mercury, pressure, volume, pressure, volume, amount, temperature, temperature. Okay, so there's all of our units. If you were ever given some of these units that are not allowed into the equation, you need to convert using our conversion practice skills in order to use a valid unit. So our valid units for pressure, there are two. We got kPa in atmosphere. For volume, you can only plug in liters. For amount, only moles. And for temperature, only Kelvin. Let's do this example together, and all ideal gas law problems are similar. They are just kind of a snapshot of the gas. They are not this before and after relationship like we saw for Boyle's law and Charles' law and Gay-Lussac's law. This time, it's like you take a picture and you see all the variables and then you solve for the one you don't know in the equation. So there's no like P1, V1 and P2, V2. It's all at one time. No before and after. So follow your units, match them up to the correct variables, and then you can plug them into your equation PV equals nRT. It says, given the gas law problem, identify which value matches each variable, determine the R value to use, and then solve. So we have question says how many moles, so that's going to be amount that we're finding, does it take to occupy 125 liters volume at a pressure of 232 kPa and a temperature of 340 Kelvin. All right, so we got all of our units. Now we need to figure out which R value to use. Well, we've only got two options. We have kPa as our pressure, so we're going to use this guy over here, which is 8.31. And that should match all of our units. Liter, yep. kPa, yep. Mole, Kelvin. So all of our units should match within this R value. Now we just plug and chug. Pretty simple. P, V, leave N as the unknown, R, and T. They already gave us all the units, so we don't need to convert to anything. Yay. So now we just solve by multiplication. If you simplify this, you get... here, let's multiply these two. 29,000. And 1,994.4 N. Okay, then we divide. To get N alone. And we've got 14.5 moles of gas, assuming ideal gas behavior. There's plugging into our equation, given the pressure, volume, and temperature of this gas, 14.5 moles. You have a few problems to practice this with on page 4. Following the same process, just make sure you are using the units that are allowed and then finding the correct R value. Write them on this left side for variables, plug them in, and solve for the correct answer.